Last lesson we looked at potential divider circuits, and today we're going to use a potential divider circuit to get some data for a current potential difference graph for a bulb. So it's exactly the same circuit that we set up last time. You've got your power supply, and we're going to split that power supply with a resistor. This is our rheostat or our variable resistor. And then we're going to put our bulb in. So we're going to connect this up to the slider. But actually I'm also going to put in, since I'm here, I'm going to put in an ammeter as well. Okay. So when the slider's right up against this end, actually my potential difference would be the potential difference of the supply. I've essentially got, when this is connected to here, I've essentially connected the bulb up to the power supply. So I've got the whole potential difference of the supply. When the slider is right at this end, actually the potential difference between here and here, it's got to be 0 because this is a lead and it's got no resistance. So I can vary my potential difference between 0 and the supply voltage. And that means that we can, when we collect data, that's what we're going to do, we can get regular intervals. So we're going to change potential difference, and we're going to measure current. And we can go up in regular intervals. What we're actually going to do is we're going to try and get negative values as well. So we're going to draw a 4-quadrant graph. So I'm going to say let's start at 12 and go down in 2-volt increments. You get the idea here, I'm sure. There we go. Okay, so we write our currents in this side. Voltmeter, of course, needs to be across here. Because we're using this circuit, we should find it easier to get these intervals. You might need to play around with the supply voltage and this, especially if it starts getting hot and you find that all your values are right up against one end, and just change the supply voltage and it'll be fine. But this circuit is much better designed for this. We're also, we're much more likely to be able to get our 12 volts. If we had this variable resistor just in series, like we would have done at GCSE, we probably wouldn't have got a value for 12 volts because the bulb and the resistor would have to share the potential difference because they'd be in series, and it's only a 13-volt supply maximum, and actually it doesn't quite get up to 13 volts. In fact, you probably still have to be lucky to get to 12 volts here. But anyway, this is the circuit we're going to set up. We're going to get data for this, and then we're going to plot a graph, and your graph, so same as GCSE, we know what we're kind of aiming for, right? This is not, hopefully not giving the game away too much here, but if we put potential difference on this x-axis and we put current on the y-axis, should end up with a graph that looks like this. Of course, if you had the axis the other way around, you'd end up with a graph that looked like that, and they might do that in an exam, so you just got to be wary. It's the current that's limited, because this bulb is getting hot, and the hotter it gets, the more those ions in the metallic bonding structure are moving around, the harder it is for the electrons to get past. And so the higher the potential difference, the hotter it gets, the lower the current. And so the current is limited. Potential difference, you can put any value you like for potential difference. I mean, you could connect this to mains voltage, it would explode, but you still managed to put 230 volts across it. So this potential difference isn't limited, current's limited. Right, we're going to then do, so I'd like you to get data, plot a graph, great. I think probably, based on my experience in the classroom, that is going to take you the entire time. It might take you longer, it might take you less time. Hopefully it will take you less time, but actually what I'm going to do is provide you with 2 lessons worth of work. So after you've done this, I'd like you to swap your bulb for a diode instead. So we're going to do exactly the same setup now. So you can leave the circuit the same really, but you're going to change the supply voltage, make it nice and low, because we're going to go up in much smaller increments. Just not put that there because I normally draw that this way. We're going to put a diode in this circuit. Now this is called forward bias, the way that I've set this diode up. The current is coming from the positive side, this is the positive side of the battery, the way to remember that is that this long line here is long enough that you could split it in half and make a plus sign out of it, or the way to remember it is this is the bold side, and so that's the minus side, because it's basically a minus sign in itself, isn't it? But anyway, the current, conventional current, of course the electrons are going to flow in the other direction, but the conventional current is this way. So come around this way and across that way. So this is what we call forward bias. So when I say that, I mean the current is flowing across the diode in the direction that the diode conducts electricity in. Now what's going to happen here actually is very quickly, this is going to get very, very, very hot, because the diode has barely any resistance in the forward bias. So what I've done is, when I've mounted up the diodes onto those bits of wood, there's a resistor. We know there's a resistor in there because we've used a resistor in the other circuit, but we're going to put there's a safety resistor in here. This is going to ruin my diagram because this is going to look like a fuse. So we've got a safety resistor in here, and that's going to limit the current. It means the current doesn't get so high that the diode basically just, well, it will smoke, and if you take out the safety resistor, the diode will just sort of smoke for a bit and then smell bad and then stop working. So please don't do that. So we set up this circuit, and what we're going to do is we're going to do exactly what we just did, but we're going to use lower values of potential difference and current, and then we're going to see then we're going to see what the voltage is that we need in order for it to conduct electricity, because it's not quite zero. So we're going to go up in, I'm kind of debating now in my head, I would say half volt intervals, and we want to get, so we're going to start at 3 volts, and then we're going to go 2.5 to 1.5, 1 and 0.5. Now, if you have been listening to me in the autumn term, you'll know that what I've done here is not allowed. So maybe pause the video and try and work out why this table is absolutely awful and I wouldn't give you the mark for it. As I'm sure you worked out, it's because if I can measure my potential difference to 2 significant figures, then I can measure it to 2 significant figures all the time. And so actually we have to have the right number of significant figures in the table all the way down. Right, even though that's the same value, and that's what I'm aiming for. Okay, good. So we're going to do that, and then you're going to then plot a graph like before of potential difference and then current. Of course, you could do it the other way around if you'd like. And then you'll find that you get a graph that looks like this, I should imagine. So the gradient of this line will actually be 1 over the resistance of the resistor, because we've got potential difference on the x-axis, remember? That's because the diode has basically no resistance in the forward bias. But it won't quite cross the origin. It should cross at about 0.6 volts, right, just about. This is something that we are going to be expected to know at A level, that it doesn't, this is called the threshold voltage. It's the voltage that we need to start it conducting electricity, and you need to know that it's 0.6 or 0.63 volts. Sometimes actually we quote it to an extra one, 0.63 volts. And that's all you're going to get from this practical. But in theory, if we had much better ammeter, and actually maybe if the ammeter, if your multimeter, if you can work out how to get it on the milliammeter setting, and the milliammeter fuse isn't broken, because actually in most of the multimeters the milliammeter fuse is just blown by someone that doesn't know what they're doing, just plugging stuff in. But if it isn't broken, you could potentially use a milliammeter with a micrometer on this and get a little bit of what I'm talking about here, a little bit of this pattern, because actually the pattern for a diode is this. So we do get a very, very, very small current up to my 0.63 volts, very small current here, and at 0 the current is 0 at 0%, but for minus values for potential difference, we get a very small negative current as well. Right, so we get a sort of trickle current. And then, and this is a sketch, this axis is not to scale, because eventually if we make our potential difference low enough, all of a sudden the diode will just break down. And this is called the breakdown voltage. Okay, so we've got the threshold voltage, and we've got the breakdown voltage, and this is about minus 50 volts, so it's quite low, but quite a large potential difference. Right? We'd need sort of 5 power packs stacked together to get this diode to break down in the negative bias, so we can't really do that, it's too dangerous, but in theory this is what would happen. And also all of a sudden we'd start getting really, really large currents in the negative direction and break all our meters as well. But that's what we would eventually see. So we do need to be aware of the whole shape of a diode characteristic graph. All right, so once we've done that, what we're going to do is some exam questions on this sort of thing. But so 2 lessons worth of work, as I say, 2 circuits, 2 sets of data, 2 graphs, and then some exam questions. So just work your way through it best you can over 2 hours. I mean, I really hope that you can do. I mean, it's basically the same circuit. So what I do actually is do your results for the bulb, your results for the diode, then start plotting some graphs after you put everything away. And actually, you could probably get that done quite quickly. And then, as I say, there's some exam questions. Let me know if you've got any questions. 2 people have already. I'm getting back to them. So keep it up and make sure that you actually are doing this work as best you can. If you are struggling to do it, you need to get some willpower essentially, because, and I know I said this last year to the year 10s and it turns out I was wrong. I said, you will definitely have exams, the year 11s won't. And actually the year 10s don't, they're now year 11s and they actually don't have exams, so I was wrong about that. But I'm not going to be wrong about this, because at year 12, you know, some of year 13, you guys will be doing exams. So, and we haven't really got time to teach the whole lot twice. So make sure that you're concentrating on this and not wasting your time. But hopefully we're doing all right. Well done everybody for the work you've done so far. Thank you.